NASA and its partners have finally unveiled data from the largest observing program conducted by the James Webb Space Telescope, JWST, to date. This endeavor encompasses an extensive panoramic view of cosmic history, comprising an ambitious survey that will ultimately integrate over 10,000 individual frames to create a comprehensive map of nearly 800,000 galaxies. The findings are challenging previously established beliefs about the early universe. The project, known as Cosmos Webb, is considered the most significant undertaking for JWST in its inaugural year. The Cosmos Webb team, which includes nearly 50 researchers from around the globe, directed the telescope to focus on a specific patch of sky, roughly the size of 3 full moons. Over an astonishing 255 hours, they allowed the telescope's advanced instruments to capture the faintest and most distant light available. The culmination of this effort is a digital mosaic that presents an unprecedented scale and depth of cosmic imagery. Previous benchmarks, such as the iconic Hubble Deep Field images, revealed thousands of galaxies in a concentrated area of the sky. In contrast, Cosmos Webb expands the perspective, akin to switching from a telephoto lens to a wide-angle lens. It does not merely illustrate the appearance of galaxies, it also provides essential context regarding their distribution and evolution within the grand structure of the universe. The unexpected abundance of early galaxies discovered in this expansive survey has significant implications for our understanding of cosmic history. The final catalog will feature detailed data on almost 800,000 galaxies, including information on their brightness, shape, and distance. This treasure trove of information will soon be accessible to scientists worldwide, fostering further exploration and research. As lead researcher Jehan Kartaltepe noted, it is uncertain whether Webb will cover such a vast area again, making this dataset a cornerstone for future inquiry. This release marks not just the conclusion of a project, but the beginning of a multitude of new research opportunities. But how is it possible for Webb to capture nearly 1 million galaxies? The James Webb Space Telescope, JWST, employs cutting-edge technology that allows it to capture images of nearly 1 million galaxies, showcasing the remarkable capabilities of this advanced astronomical instrument. At the core of Webb's functionality is its impressive 6.5-meter primary mirror, which is the largest mirror ever launched into space. This mirror is composed of 18 hexagonal segments made from beryllium, a strong yet lightweight metal. Each segment is coated with a microscopically thin layer of pure gold, which is specifically chosen for its ability to reflect infrared light, a crucial aspect of Webb's design. As the universe expands, the light emitted by the most distant galaxies gets stretched, shifting visible light into the infrared spectrum by the time it reaches Earth. This ancient, red-shifted light remains invisible to human eyes and even to previous telescopes like Hubble. JWST is engineered to detect this infrared light, providing insights into the early universe. To observe these faint signals without interference, the telescope operates at extremely low temperatures. Any heat emitted by the telescope would create an infrared glow that could obscure the faint signals it aims to capture. To address this challenge, engineers designed a 5-layer sun shield roughly the size of a tennis court. Each layer is as thin as a human hair and effectively keeps the telescope's mirror and instruments at a chilling -223 degrees Celsius. This cold, stable environment enhances the functionality of Webb's key instruments, particularly the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI. NIRCam captures high-resolution images that serve as the foundation for the panoramic views, while MIRI observes longer wavelengths, allowing it to see through cosmic dust. The combination of a large gold mirror, extreme cooling, and sensitive instruments enables JWST to produce stunning images that continually surprise researchers. These images serve not only as beautiful visuals, but also as scientific databases. Astronomers are already using the information gleaned from these images to make groundbreaking discoveries that challenge our understanding of the universe's early history. Traditionally, the timeline of the universe has been framed around the Big Bang occurring 13.8 billion years ago, followed by a cosmic dark ages characterized by a neutral hydrogen fog that absorbed the light from the first stars. The prevailing theory posited that galaxies gradually emerged over hundreds of millions of years, piercing through this fog in a process known as reionization. However, findings from JWST are revealing galaxies that challenge this established timeline. One significant discovery, made through a program known as JADES, involved the identification of a galaxy named JADES GS Z13-1, which existed a mere 330 million years after the Big Bang. Notably, this galaxy emits a bright hydrogen signature that theoretical models suggested should have been obscured by cosmic fog. Researchers have expressed astonishment at these findings, with one team member describing the results as totally unexpected. This is akin to discovering a fully grown tree in a landscape where only the initial seeds were anticipated to exist. The data suggests that this galaxy had formed a significant, clear bubble around itself, a phenomenon that current theories indicate should have taken a much longer time to occur. As one researcher aptly noted, we really shouldn't have found a galaxy like this. These early galaxies appear to have been not only larger, but also more powerful than previously believed. Every grand astronomical structure, such as the Milky Way galaxy, has origins that can be traced back to specific events in cosmic history. Surrounding our Milky Way are approximately 150 globular clusters, which are ancient collections of millions of stars. A key question arises: when and where did these clusters form? Recent advancements with the James Webb Space Telescope, JWST, may provide vital answers. In observations of a distant galaxy referred to as the Cosmic Gems Arc, which existed just 460 million years post-Big Bang, the JWST identified 5 remarkably young, massive, and dense star clusters. Scientists believe these may be protoglobular clusters, representing the initial building blocks of the structures we observe today. The lead author of the study expressed the astonishment experienced upon viewing the JWST images for the first time. These clusters exhibit an impressive degree of compactness, significantly denser than any star-forming regions detected in our local universe. This marks the first direct evidence that the origins of giant star clusters were established during the universe's early stages. This finding is critical in piecing together how our own galaxy began forming. Despite its capabilities, the JWST is unable to resolve individual stars in galaxies that are billions of light-years away. Such distant galaxies typically appear as indistinct smudges of light, making it seem impossible to identify a single star within them. Remarkably, however, Webb has achieved this feat. The key to this remarkable capability lies in a phenomenon known as gravitational lensing, which was predicted by Albert Einstein over a century ago. When a massive object, such as a galaxy cluster, warps space-time, it can bend and magnify the light from objects situated behind it, functioning akin to a natural cosmic telescope. This process can amplify light by thousands of times. While astronomers have employed this technique previously, the exceptional sensitivity of the JWST has elevated it to new heights. The telescope has enabled scientists to detect individual stars at extraordinary distances, including a star named Earendel, recognized as the most distant single star ever recorded and observed, as it was nearly 13 billion years ago. This achievement is comparable to identifying a solitary firefly from the other side of a continent. Beyond merely setting records, the study of these magnified stars allows scientists to map the distribution of dark matter within the lensing cluster, thus providing new insights into both early stellar formations and the enigmatic substance that constitutes the majority of our universe. One of the most important aspects of the Cosmos Webb project is not just what they discovered, but how they're sharing it. The team made all the data, including images and a large catalog of galaxies, publicly available for free. They even created an interactive online viewer so anyone, whether a researcher or a curious student, can explore this new area of study. This is significant. The raw data from the Webb telescope is complicated and often takes research teams a long time to sort through. By cleaning it up and putting together a ready-to-use catalog, the Cosmos Web team has made it easier for everyone to access the secrets of our universe. As one researcher said, it was all worth it because ultimately it has delivered some of the highest quality data that will enable groundbreaking science. The impact of this is huge. We are entering a time when discoveries are not just for those who have telescope time, but for anyone with a good idea and an internet connection. So what's next? The Cosmos Web Survey is just one part of Webb's mission. Every day it sends back more data, reaching farther back in time toward the Big Bang. The findings discussed today are just the beginning. We are just starting to explore a new cosmic ocean. The universe tells a story through light, and with Webb, we've learned to read a new language. The data will keep scientists busy for years, and we will keep you updated on the biggest discoveries. Subscribe now to see new highlights as they come. Since the beginning of our existence, curiosity has defined us. We look up at the night sky and feel connected to something much larger than ourselves. For a long time, we could only see a few bright points in the darkness, but that has changed. This new view from Webb offers more than just data. It gives us a new perspective. Seeing hundreds of thousands of galaxies, each with billions of stars and possibly trillions of planets in a small patch of sky, is humbling. It changes everything. Every conflict, every success, and every moment of human history has happened on a tiny speck of dust orbiting one star among many visible now in one galaxy among thousands. Yet this image does not make us feel small or insignificant. It is deeply inspiring. It shows that the universe is not empty and cold, but lively and full. We are just starting to understand this richness. The same laws of physics that created these distant galaxies created our world and our bodies. We are made of stardust. We are the universe's way of knowing itself. With this new view of the sky, our understanding of the universe and ourselves will never be the same again.